All right, so you know how we always picture atoms like little solar systems? You know those Bohr models from way back? Electrons whizzing around the nucleus in perfect little orbits? Well, get ready to have your mind blown. Because today, we're diving into a paper that's totally shaking things up. We're talking a complete reimagining of the hydrogen atom.
Yeah, it's funny, right? We get so used to those classic diagrams. But what this paper really makes you question is the electron itself. Like, what if we've had it wrong this whole time?
So are you saying electrons aren't those tiny particles zipping around? Because that's how I always think of them.
It's more like we're used to this story of the electron as a particle, jumping between energy levels like it's no big deal.
Right, like some kind of quantum kangaroo or something.
Exactly. And those quantum leaps always mess me up.
Don't even get me started. 1 minute the electron's here, the next it's over there. No explanation, no in between.
Totally. It's enough to make your head spin.
So if those classic models aren't cutting it, what's this paper saying is going on?
We're proposing something way more elegant, if you ask me. What if instead of a particle, we think about the electron as a wave?
Okay, hold on. Now I'm really lost. I thought electrons were like things. You know, little bits of electrical charge. How can they be waves?
Okay, so think about it this way. We know electrons have properties, right? Like charge and angular momentum. This paper explores the idea that these properties aren't stuck in one spot. They're spread out like a field. Like imagine a ripple on a pond. That's our electron wave.
So instead of a tiny ball, it's more like a ripple. But a ripple that carries electricity.
Exactly.
That's a pretty wild way to picture it.
It is wild. But it helps explain some of the really weird things we see at the atomic level. And when you apply this electron as a wave idea to the hydrogen atom, things get really interesting.
Okay, I am officially hooked. Tell me everything. How does this change how we see the hydrogen atom?
All right, so buckle up, because we're about to compare the hydrogen atom to something you use all the time, a resonator.
Like a what?
A resonator. You know, like how a certain whistle tune makes a dog freak out?
Yeah, because it like resonates with their ears or something.
Exactly. It's all about resonance. And this paper suggests that something similar is happening inside the atom.
Wait, you're saying the hydrogen atom is like a tiny musical instrument or something?
Kind of. So picture this. The nucleus with its positive charge. That's like the walls of our resonator. And the electron wave with its energy and wavelength, it can only exist within those walls in specific ways. Stable states, like trying to fit different standing waves inside a guitar string. Only certain wavelengths are going to create those resonant tones.
Okay, so instead of the electron randomly jumping between orbits like in the Bohr model, it's more like it's vibing at different frequencies. But only certain frequencies work within the atom's own little space.
You got it. And that's how this model explains the distinct lines we see in the hydrogen spectrum. Each line is a specific frequency of light, emitted when the electron wave transitions between those resonant states.
So, this is blowing my mind. Thinking about the atom like a tiny little instrument. It makes so much more sense than those quantum jumps. But if this is how it works, what about all that other weird quantum stuff? Like spontaneous emission. How atoms just randomly decide to shoot out light.
Right. Well, that's actually where this model really comes in handy. It explains spontaneous emission in a way that's just makes sense.
Really? No more randomness?
No randomness needed.
Okay, tell me more.
So we've got the electron wave, right? It's just oscillating in its little atomic resonator. And anytime you have an oscillating charge, it naturally radiates electromagnetic energy, just like a tiny little antenna.
So no spooky quantum leaps, it's just good old-fashioned physics.
Exactly.
So this one little change, thinking about the electron as a wave, explains one of the weirdest things about quantum mechanics.
It's pretty cool, right? And this paper takes it even further. It uses classical physics equations to predict not only the frequency, but also how much light the hydrogen atom should emit. And guess what?
Right.
It lines up perfectly with what quantum mechanics predicts.
Whoa, so this isn't just some abstract idea, it's got real predictive power.
Exactly.
Okay, so we've talked about the electron as a wave, we've talked about spontaneous emission, but what about those forbidden transitions? That's always sounded so weird to me. Like there are rules about what kind of light atoms can't emit.
Right, so this is another area where this model gives us a new way to think about things. Basically, It says those transitions aren't actually forbidden, they're just impossible.
Impossible, like trying to make a square circle impossible.
Yeah, exactly.
Yeah.
Remember how we talked about the hydrogen atom being like a resonator, where only certain electron wave frequencies can exist, while those forbidden transitions, they correspond to frequencies that simply can't fit inside that atom.
Ah, so it's not that the atom is being blocked from emitting that light, it's that that light just straight up can't exist in that space.
Precisely.
Wow. Okay, this is all mind-blowing. But I'm still stuck on one thing. We keep talking about single atoms, but in real life, experiments are dealing with trillions of them, right? So how does this electron as a wave idea explain the statistical nature we see when we look at those huge groups?
That is a great question. And it gets to one of the most interesting parts of this paper. Basically, it suggests that the randomness we see in quantum mechanics, it might not be as fundamental as we thought. It might just be a side effect of looking at so many atoms at once.
Hold on. Are you saying quantum randomness might just be an illusion?
That's what this paper is suggesting. Think of it this way. Imagine a huge field of sunflowers, each one tilted towards the sun in a slightly different way.
Okay, I can picture that.
Now, if you're far away, you might think they're all just randomly positioned. But if you could zoom in on each sunflower, you'd see that each one's angle is determined by all sorts of factors, like its history, how much sunlight it's got, and the wind, all of that.
So you're saying even though individual atoms may be predictable, when we look at a ton of them at once, it just looks random.
Exactly.
So it's not really random at all. It just looks that way from a distance.
That's the idea. This paper argues that if we could track every single atom, we wouldn't see any randomness, just electron waves behaving exactly how we'd expect, according to the laws of physics.
Wow. It's like this paper is turning everything we thought we knew about atoms on its head. It's a lot to wrap your head around, but it also makes things strangely reassuring.
Definitely. And like you said, it raises a ton of new questions. If this electron as a wave thing is right, what other quantum mysteries could it solve?
Right. It's like we've been staring at this giant puzzle.
And this paper just gave us a crucial missing piece.
It might not be the whole picture, but it gives us a whole new way to see how the pieces fit together.
Totally. And like with any good scientific discovery, this one comes with its own set of new mysteries. For example, the author points out something really interesting. The electron wave doesn't seem to interact with its own electric field.
Wait, really?
Yeah, it's like it's only paying attention to the field from the nucleus.
That is super weird.
It is. It's like each electron wave is so busy doing its own thing, it doesn't even notice itself.
So another mystery to solve.
Exactly.
Yeah.
Which just shows you how much we still don't understand about the quantum world.
That's the beauty of it, though, right? Always more to discover.
Absolutely.
Well, I think we've given everyone a lot to chew on today. If there's one thing to take away from this deep dive, it's that those neat little atom diagrams we all learned in school, yeah, they might not be telling the whole story.
Definitely not.
The quantum world is full of surprises, and the more we learn about it, the weirder and more wonderful it gets.
Couldn't have said it better myself.
So until next time, keep those questions coming. And we'll keep diving deep into the mysteries of the universe.